Good morning, and welcome back to Physics 4B Lab. We've finished up with our thermodynamics labs. We've been looking at electric forces, electric fields in class now for a bit, and we're going to be looking at our first electric force lab. So, and we're going to call it the electric force lab. The objective today is to be able to measure a certain amount of charge. Now, this is what we're going to be looking at is often referred to as static electricity, and you know, you're used to, if you comb your hair or if you pull the clothes out of the dryer, there are these attractive forces that that you observe, and that comes from transferring electrons, in particular, from one material to another. Well, we've got a bunch of different materials here. We've got different sorts of cloth. I don't know, this looks like a red polyester or something. There is some silk. We've got some different types of plastics. So we're gonna, and we have some fur also. So we're gonna try different combinations of materials, and we're gonna see how much charge we can transfer using those materials. Now we need a way to go in and be able to measure this, and so what we're gonna use is this setup here. Now I know this is at a bit of a distance right now. We'll do a close-up here in a bit. We've got some stuff up on the board. But what I have here are a couple of, well, very thin threads. And at the end of these are these little cylinders of what's called pith. It's a dried plant material, and it's very low density. So the masses on these two are really small, the blue and the green object that we have here. In any case, the way that we're going to be able to go in and actually measure a certain amount of electric charge, and we're going to count how many electrons we've transferred. We're going to do that by charging these pieces of pith. And so let's see what that might look like. I'm going to grab this piece of red cloth and one of these pieces of plastic. And you can see it has an immediate effect. And so what just happened there? And as we've talked about in class, when we look at materials, there's protons and electrons and neutrons that make up the atoms and molecules inside a material. The protons are positively charged, the electrons are negatively charged. And when we talk about objects having a positive or a negative charge to them, something that has a positive charge, you know, if I have a piece of cloth and it's got a positive charge on it, that's because it's missing, in some sense, some of the electrons. Most materials around us have almost equal numbers of protons and electrons. And that means that there's no net charge. But through just static electric sort of effects, you know, by rubbing this cloth on this piece of plastic, we're actually able to transfer some electrons, and I don't know exactly which direction is which here. Let's say, for example, electrons are being transferred out of the cloth and onto the piece of plastic. Well, that's going to leave the cloth positively charged. It still has all of its protons, but now some of the electrons are missing. Meanwhile, over on the piece of plastic, this now picked up those additional electrons, so it has more than enough electrons to be electrically balanced. So we'll end up with positively and negatively charged objects. Now what we just did with these pieces of pith is, let's say for example, I rub this, and that builds up additional extra electrons on this piece of plastic. I can then bring that over to these pieces of pith in the string, and some of those electrons, not all of them, but some of those electrons are going to transfer over. Now, this gives us something that's actually measurable, if I can get these two pith cylinders to separate. Here we go. This is one of the real challenges of doing this lab. All right. Yeah, I think I've got them. Okay, so the idea here again, transfer some of these electrons out. And if we've successfully transferred electrons to the two pith cylinders. What I should be able to do now is remove everything away. So what we're going to measure is just the electron transferred into those pith cylinders. Now if you look at this now, they've separated. There's a little bit of repulsive force. Both of these have picked up, let's say, a negative charge. Let's say we transferred electrons into both objects, and now they're repelling each other. So negatives will repel each other. So the force diagram for this looks something like what we've got on the board here. What I've got is I've got a support object up here at the top. I've got these pieces of thread. Now we're ignoring the mass of the thread. And I'm never quite sure about that. The pith itself doesn't have much mass, so the thread could be significant. We should probably put that on a scale and see how that compares. But we've got some thread. Here is the pith, and what's happening then is if I look at one of these, I'll look at this one right here. So I'll isolate the one on the right in my diagram and say this one has an electric force acting on it, has a gravitational force acting on it due to its mass, and then there's a tension in the thread, or a tension in the string. Now, if I use the left one, the one on the left side, I'm going to get the same force diagram, or kind of a mirror image. And you remember from Physics 4a, when I'm doing force diagrams, we haven't done these for a while, right? We've been looking at thermodynamics mostly. We're back to looking at force diagrams. We've got the electric forces pushing these objects away from each other. They each have a gravitational force, they each have a tension, but to analyze the force diagram, we really just want to isolate one object. So that's what we've done. So I can ignore one of these, just focus on this one. Now I've taken the forces here, and I've drawn this onto a coordinate system. So this is pretty standard stuff from Physics 4a, right? So now I've got a coordinate system. And I've got a tension, and the tension is acting at an angle. So I've drawn an angle theta. We're going to have to be able to go in and measure that on the experimental setup. So I've got this angle drawn here. And what that's doing is it's taking the tension and dividing it into a cosine component that's vertical and a sine theta component that's horizontal. And that's based on where we've defined the angle. So we're going to define the angle as this opening angle at the top, just on one side. So there's a theta on this side, and there's a theta over here on the other side. And again, we're just focusing on half of this diagram. Here is the electric force. Now that's going to be in the horizontal direction. And then I've got a gravitational force, and we're going to place that in the vertical direction. Now we know from Physics 4a, the gravitational force, we can write that as mass times the gravitational field, and then we can just use the gravitational field for Earth. So we'll write that in, right? We'll say, hey, gravitational field, this lab is being done on planet Earth, so that's going to be 9.80 newtons per kilogram. Now, newtons per kilogram, those are the same units as meters per second squared. But when we're thinking in terms of a gravitational field and how much force is being generated, it's more useful. Instead of using meters per second squared, let's use newtons per kilogram. Okay. So if you guys have been in my Physics 4a class, that's one of the, flexibilities that we say is important to be able to switch back and forth between equivalent sets of units as needed. So, or as is useful. So here's the Earth's gravitational field, and let's see, what other items do we need here? We've said in chapter 21, one of the first things we introduced was the electric force formula. Now this is the force acting between two charges that are at rest, separated by some distance. And so now there's an electromagnetic force constant, and I've written that down here. So that is the force constant for all electric effects, all magnetic effects, everything we look at in the next 12 chapters of the book and beyond, actually, throughout the rest of the book. Anytime there's an electric force or a magnetic force, that can be expressed using the electric magnetic force constant. All right, now, when these two separate, I guess what we need to ask ourselves is, how much charge is on each object? Now, if you think back, the way I was trying to transfer charge here, I was trying to run that piece of plastic along both strings and both pieces of pith in kind of a symmetric fashion. And the reason why is, as best possible, I want to transfer the same amount of charge to each object. So we're going to go ahead and assume for this setup that Q1 equals Q2. Both objects acquire the same amount of charge. Now, that doesn't have to be the case, but we really don't have a way to solve everything going on here unless that's the case. So I tried to run the experiment in a fashion where the charges would be very similar to each other. Even if the charges aren't the same, let's say that Q1 is bigger than Q2, the force diagram is going to look the same. We're going to have the same forces in both directions. Each object will still have the same amount of force acting on it. So we'll still have the same angle here, as long as they have the same mass. It really doesn't matter how the charges divide up. So again, we're going to try and create, as best we can, the likelihood that the charges are equal on each of the pieces of pith. So this is what our force diagram looks like. Now, there's a number of ways we could kind of go through the formulas. So, you know, I just picked one particular way that I thought would be useful to go in and think about the formulas that we have here. So what I did was I took the two tensions, the two components, and I eliminated t. So t sine over t cosine is tan theta. Now if I look at my diagram, it turns out these objects, they're not accelerating, right? What they've done is they're pushing away from each other, but there's no acceleration taking place, and if there's no acceleration, then the forces have to cancel out. So that tells me that t sine theta and the electric force are the very same value. And t sine theta and the gravitational force, they're the very same value. And we never really are interested in what the tension is in the string. At least I'm not going to ask that. So we're going to use this expression to eliminate t. And now what I'm showing with my formula is that there's a ratio between the electric force pushing them to the side and the gravitational forces pulling them downwards, and that ratio is going to be given by the tangent of whatever the angle is. So that's measurable. We can go in and measure that angle. In fact, this next formula is actually measuring that angle. What I've done is I have taken out one of these right triangles and drawn it. Now the hypotenuse is going to have a certain amount of length to it. So I've got some rulers up here, and I can get a measurement. Oh, that's pretty, it's just barely going to reach. I got to get a different ruler, or I got to change the string positioning. So right now it's just a little bit beyond 30 centimeters of length. Now I've also placed the strings, if you notice here, I've got some masking tape on here, and I've masking taped the strings on. I want the strings so that they're coming from one point. And the reason I want the strings to be both supported from the very same point is that's what my force diagram looks like. Right? I got to make sure that my experimental setup, the apparatus that we put together here, matches the diagram that we're using for our force diagram. If one of the strings is attached over here and another string is attached over here, it would be a different force diagram. So anyway, I got a couple things I'm going to have to change here when we do the close-up. I want to make sure, because the strings aren't quite next to each other yet, I want to make sure the strings are right coming from the same location. And I got to shorten the strings a bit, otherwise I'm going to have to go get a different ruler. And I do want to be able to measure down to the millimeters and even estimate fractions of a millimeter from this. Now that raises another question: is when I have an object like this, what location do I measure to? And you know what we're going to do is we're going to measure from the center to center. So we're going to identify, we're going to estimate the centers on these. So yeah, a millimeter, if we can measure to a millimeter, we're going to be doing pretty good. So I'm going to measure from this pivot location down to the center, what I'm estimating is the center, and say that's my L value. And then what I'm also going to do is, once these things are pushing away from each other, I'm going to measure center to center to find out how much distance of separation we've got. Okay. And it turns out, the best we do is not more than just a few centimeters. So you can see why we really need something that's low density, something with a really small mass. It turns out that, these little pieces of pith pick up, a certain amount of charge, but it's not so much to create a huge force. So we want to keep the gravitational forces small. All right, so we've got these, this is telling us, the sine theta, I guess we do need to talk about that a bit. The sine of theta is going to be this side, which is 1/2 d. So I'm going to measure d, and it's in my data table over there, divided by L. So I'm using the definition of a sine. This is the opposite side over the hypotenuse. 1/2 d over L, that's going to work. So let's say that we do, in a data table, let's say that we have the cloth. I know that's not very specific. Let's say that we have cloth, I think it's polyester. And what was the other item we had here? We had the clear plastic. Now this is just one entry. What we want to do is we want to try, 4, 5, 6 different combinations here. What we want to do is take different materials, and we'll measure what the L is. I'm just going to put some made-up numbers here. These aren't the actual measured values yet. Let's say we measure this, and it's 31.2 centimeters, and we put a distance value in here, and the distance value is 3.6 centimeters. That would enable us to calculate the opening angle at the top, and then we also need to get a measurement of the mass. We'll figure out what the mass is going to be given by. Calculate the gravitational force, and then we can calculate the electric force using this formula. Let me write a few things in here. So I'm going to say, I think the L is probably going to be in centimeters. The D is probably going to be in centimeters. It's probably going to be in degrees. Now the force of gravity, I guess we'll put those in newtons. We might as well stick with, excuse me. We might as well stick with standard units of newtons. Now for the electric force, I'm expecting that's also going to be in newtons. But let's do this. Let's say that the way we're going to calculate the electric force is going to be from this formula. So the electric force, I'm going to calculate that from Fg times the tangent of theta. So that's the formula being used. I'll draw a little arrow here. So for that column, that's the formula I'm going to be using. Fe equals Fg, tangent of theta. Now, we also want to calculate how much charge. In fact, that's kind of what our goal was for the day. And then it's going to be in coulombs. So I hope you guys are getting familiar with these units for electric charge or magnetic charge. Same thing. When we talk about electric charge or magnetic charge or electromagnetic charge, it's all the same thing. There's just that one charge value that tells us how this object is going to respond to electric and magnetic effects. All right, so that's in coulombs. Now in this last column, what I've included in the data table, and let's go ahead and do this, is the number of electrons. So for this, what we can say is that the number of let's go back up to here. The total charge that we've transferred is going to be some number of fundamental charges where the fundamental charge is 1.60, 10 to the 19, let's get that changed, minus 19, sorry, that needs to be updated. 1.60, 10 to the minus 19 coulombs. So that's the charge on a proton, or it's the amount of charge on an electron. And so the total charge of any familiar object around us is going to be some number of those fundamental charges. It's going to be based on how many electrons or how many protons charge that we're dealing with in that problem. So to calculate the number of electrons, we're going to take the total charge and divide it through by this fundamental charge. Now that raises an interesting kind of question is, when you have a static electric effect, how many electrons do transfer? Now this is small, these are just these little tiny pieces of pith. But even here, I'm guessing we're going to see billions, with a B, billions of electrons transferring into these objects. So that's a lot. That's a very large number, right? Well, that's kind of the story here. So once we get, we'll do these runs, and again, we'll come back and do a close-up of this, but we will, we'll just try a few runs and write down some distance of separation that we've got here. We'll double check the L values. The L values could change if we end up repositioning the strings. Once we've gotten, a few runs with different combinations of materials, that's kind of the idea. So I'm guessing it's a really good lab to start building up a conceptual understanding of how these electric forces work. But not too many details. So enough things to stop and think about. But once we've got this table filled in, that's it. There's not any accepted values to compare with, and so in our results, if we call this a data table, and it looks like we just need the one data table with many entries. The results table. The results table is just going to be materials and the amount of charge. And I guess we could put in the number of electrons. Okay, that's what we set out to measure. So the results table, we're going to skip all the intermediate values and just write down how much charge and how many electrons that corresponded to. So if there's any questions, stop by the lab hours or office hours, or they're all kind of the same thing. Stop by ConferZoom and let's get those questions answered. All right, here we are with the close-up. Now, what I've got here is I've got some of these pith objects, and what we find is if I put one on the scale. Now, these are our sensitive scales. Chemistry might have some better ones. Maybe I should have borrowed one. But right now, what it's saying is this is somewhere between 0.04 and 0.05 of a gram. Well, that's a problem, because if it's 4 or 500ths of a gram, and I'm off by 100th, that could be a 20 or 25% error that we're coming up with. So I kind of had I wasn't sure what to do about this. What I ended up doing was I took 10 of these. So the idea was to take 10. Now when I took 10 of these, it gave me what's probably something more reliable. What it's giving me is 0.59 grams. That gives me two significant figures. So this is going to be a more reliable number than just measuring one of them. The problem now is, are these representative of the ones that are actually hanging up here? These are kind of larger. There is some variability in size here. I tried to pick out ones that were kind of on the larger side of things. But I'm going to go ahead and go with this, I guess. What I'm going to do is use this. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so I did count 10, and I am getting 0.59. Yeah, it came right back to that. And now I'm not having quite the uncertainty. Okay, I am going to grab some paper, start writing some of these numbers down. And so for the mass, I am seeing 0.59 grams, and that's for 10. Okay, so that was one of the items we had to make sure that we got taken care of. Now, the next item here, I've got to reposition these real fast. So let me take a quick break. I'll come right back. Let me get this repositioned. Yeah, maybe I'll just leave this on. So what I wanted to do was a couple of things here. I wanted to shorten the string just a bit, and then I wanted to make sure that the strings were coming from the very same vertex. So that looks better in terms of the vertex. And the string is a little bit shortened. Now it looks like they're both, the threads are about the same length. So I do want to get a measurement on that. And let me grab the ruler. So I've got the ruler, and from the vertex down to the center, I'm measuring that at 28, I'm going to say 28.3. So I'm going to say that L, 28.3 centimeters. All right, here is the challenge now. The challenge is, let's see, what were some useful materials from before? The challenge now is getting some of this. Whoa, okay. So there's definitely a static electric effect here. We definitely have charges transferring around. Now, remember, I can't leave this piece of plastic here because that's not included in my force diagram. And even though there was a lot of charges there, we didn't end up transferring anything long term. I've got to come back and see if I can get some of this transferred. Now this time it does look like, at least initially, we had some charge transfer taking place. Okay, now that's what we're after. I'm going to try and get this measured quickly. Now if I bring the ruler too close, that's going to cause problems. So this is a bit of an estimate too. It's not our most highly precision. Okay, my best measurement here is 2.4. I'm going to go with 2.4. So it's not an especially high precision lab, but we are going to get a good estimate as to how much charge can successfully be transferred. Now, this kind of wrapped around itself here. Let me go back and try this one more time, see if we can get this transferred without quite so much uncertainty. Yeah, so it seems like the charges are not staying put. I'm trying to make contact with both strings here. Okay, and so again, that looks like a couple centimeters of separation, and it looks like we have a good vertex there. 2.1 is now my estimate. I'm going to write both of those down. I wasn't sure if I had a good look at that vertex from before or not. Anyway, what I'm going to do now is I'm going to go through and I'm going to try different combinations of these materials. So I got some PVC, we've got some different fur. I may take a comb through my hair and see if that is successful. There's some silk. So I'm going to try a bunch of different combinations, and we'll see how the distances compare. Now, as I was saying before, 2 or 3 centimeters is about as well as we do. It's not a huge force, but it's something measurable with the setup that we have. All right, questions on this? Let me know. Stop by office hours, and let's get this all figured out. All right, have a good day. Bye.